Hello, in this video I'll explain to you how to solve problems related to alternating current circuits. For example, how to determine the voltage in a circuit that has both an inductor and a capacitor. Before we begin, we must understand the fact that, unlike direct current circuits, in these circuits we'll be working with complex numbers due to how certain components like inductors and capacitors have a phase angle of 19 and minus 19 degrees with respect to the current. What this means is that in case of the inductor, the voltage will reach its peak value before the current does, while the capacitor will reach the peak value after the current. In electrical engineering, we use a J to symbolize imaginary numbers instead of an I to avoid confusion with the current. This will affect the way we calculate the total resistance in a circuit, but now we'll refer to the total resistance of the circuit as impedance. But here's the catch. We now must also include the reactance to calculate the impedance. And what is reactance? Well, it's the opposition to the flow of current that capacitors and inductors present. So basically, reactance is the resistance that a capacitor or inductor has. The way to calculate the impedance is the same as we would calculate the total resistance in a direct current circuit, by adding the position to electric current that each component presents. But how do we calculate the capacitors and inductor reactance? Let's analyze the following circuits so it's easier to understand and you can see the whole process. As you can see, we have a circuit with a resistor, an inductor, and a capacitor. The voltage source is one of 20 volts and a frequency of 15 Hz. The capacitor has a value of 2 farads while the inductor has one of 3 henries. Now, we want to calculate the total impedance of this circuit, and to do that we need to convert the values of both the capacitor and inductor to ohms. We do that by using the formulas on screen. The F will represent the frequency of the voltage source, while the L and the C represent the values of the inductor and capacitor respectively. I'll be rounding up some of the values to make it easier to follow along, since there will probably be a discrepancy of around 2 decimals for the final values, but nothing that significant. Let's start by converting the capacitor. We substitute the formula with our actual values, having a frequency of 15 Hz and 2 farads for the capacitor. When multiplying 2p by the frequency, we must be careful and express the result in radians, since this is the unit of the angular frequency, which is the result of multiplying these two. We get approximately 94.25 radians, so we multiply that by 2 and get 198.5. Now to obtain the reactance, we just do the division on screen and obtain a total of 0.0053 ohms for the capacitor. We must not forget to add the degrees next to the reactance value. Since this is a capacitor, its phase angle will be minus 19 degrees, as shown before. Moving on to the inductor, we again substitute the values and express in radians the result of multiplying 2p by the frequency. We obtain around 94 radians again, so we multiply that by 3 and get a reactance of 283 ohms with a phase of 90 degrees. After this, we get the following circuit. The rest of the process is easy, we just need to add all these values to get the total impedance, getting the following equation. We can convert the values of the capacitor and inductor to complex numbers in the following way, so we can end up using the corresponding formulas to find the total impedance. We do these direct conversions only when the angle is either 90 or minus 19 degrees, since there is a formula for converting values that have distinct degrees, but we'll see that in the next video. Now we can add the values of the capacitor and inductor so we get this equation. The following step will be using this formula to convert these values to impedance. Here, R will be the resistance with a degree of 0, while X will be our imaginary part, which we already calculated. On this other side, phi will represent the phase angle of our impedance. To obtain it, we need to divide the imaginary part by the real part and then calculate the arctan of that number so we obtain the phase angle. We just follow this formula and end up with 284 ohms for the final impedance. With this formula, we divide the imaginary part by 23 and obtain its arctan. In this case, we actually set the calculator on degrees, so we don't make the mistake of getting a result not expressed in degrees. So there you go, that's the total impedance for this circuit. If we wish to get the value of the current, we just divide the voltage by the impedance. In this case, the current will be 0.07 amperes, with a phase angle of minus 85 degrees. This means that the current is lagging behind the voltage and thus the voltage will achieve its peak value first. Let's say we want to calculate the voltage of the inductor. We do that as we would in a direct current circuit where we multiply the current by the resistance of an element. Here, our current is 0.07 amperes with a phase angle of minus 85 degrees. We need to multiply that by the reactance of the inductor, which is 283 ohms with an angle of 19 degrees. We just multiply the current value by the 283 ohms to obtain the voltage value. In the case of the angle, we add them, getting a phase angle of 5 degrees. So the final voltage for the inductor is 19.81 volts with a phase angle of 5 degrees.